Bonjour. That's the extent of the French. You don't want to hear any of the rest of my French. So this is a talk about Java in the modern era, where change is the only constant. In the past couple of years, we've changed the Java platform in 3 ways that we never have before. First, we took this massive monolithic platform that had grown monotonically over time, and we sliced it up into 26 standard modules. Second, we removed the Java EE and Corba modules and some other APIs, leaving us with 19 standard modules. And third, we left behind our historically grand and majestic but somewhat unpredictable release model in which we shipped a major release every 2 to 3, maybe 5 years, and we replaced it with a rapid cadence model in which we ship a new feature release every 6 months on a strict time-based schedule. Now, modularizing the platform and removing some modules did break a few things, and many have wondered whether the Java ecosystem will be able to keep up. Taken together, all of these changes are, frankly, somewhat scary, but maybe they're not as scary as you think. Why did we make them? Because adapt or perish now as ever is nature's inexorable imperative, according to H.G. Wells. Or in a more modern formulation, adapt or die. So saith Andy Grove from Intel. We must change Java in new ways because its competitive environment is very different than it was 20 years ago. There have been 2 big changes. First, many popular platforms now ship new features around once a year, if not every 6 months. If Java is to remain competitive, then we must move it forward faster. Second, applications are packaged and deployed in different ways than they were 20 years ago, whether to the cloud or in packaged apps published to app stores. If Java is to remain competitive, then we must adapt it to these new environments. Let's look at the first big change, modularizing the platform. This is where we ended up, a nice, clean module graph, 26 standard modules. The Java base module there at the bottom, that's the one that you always have. It's got essential things like Java lang object and Java lang string in it. It's the one module upon which all other modules depend, and it depends on no other modules. The JDK has these standard modules, plus a bunch of other non-standard modules that contain development and debugging tools, service providers, and various JDK-specific APIs. This beautiful graph is not where we started. Where we started was with this. A spaghetti bowl of tightly coupled platform components with some sometimes surprising interconnections. It turned out in this original graph, if you traced all the dependencies, if you looked at the code, the components that you needed to invoke system.println hello world, you would trace all that out and you would wind up including Corba. Okay. Slicing all this up while maintaining as much compatibility as possible took years of painstaking refactoring and very delicate surgery. We were finally able to deliver on that in JDK 9. Now, modularizing an old code base can be a lot of work, but modularizing the platform yielded many benefits. One benefit is that it's more flexible. A module names the modules upon which it depends, so the compiler and the runtime system can ensure the reliable configuration of consistent subsets of the platform. Most applications, after all, don't need all of these modules. If you have an app that only uses Java SQL and the base module, then you can link a custom runtime system that contains just those modules plus any others that they need. All the rest just falls away. You can package this custom runtime system with your app, resulting in smaller Docker images and smaller App Store packages that are tens of megabytes rather than hundreds. Now, to take advantage of this, you don't need to modularize your app. You can do that if you want. There are many good reasons to do so, but it can be an awful lot of work. And if your app is essentially in maintenance mode, it's probably not worth the trouble. Another benefit of the modular platform is that it's more secure. A module exports only specific packages for use by the modules that depend upon it. That way, the compiler and the runtime system can enforce strong encapsulation. How much more secure is it? Of the 6 high-impact, zero-day vulnerabilities reported against Java since JDK 7 in 2011, 3 of them would have been prevented if we'd been able to encapsulate the internal APIs of the JDK. A final benefit of the modular platform is that it's easier to maintain. The JDK does have many internal APIs that were never meant to be used by external code. For decades, we've been warning developers, don't use them. Please don't use them. They've done that anyway, of course. Anybody in the room? No? No. Oh, yeah, okay. A few are brave enough to admit it. Sometimes they've done this in some extremely popular libraries. Now, to be fair, in some cases they were after critical functionality that was available in no other way. Okay, so fine. But in many cases, they were just lazy. We can all be just lazy. I mean, why write your own base64 decoder when there's a perfectly good one over in SunMISC? Just use it, it works. For 20 years, we've therefore treated many internal APIs as if they were standard. We've been reluctant to change them because we don't want to break people's code unnecessarily. But this has made the platform harder to maintain and harder to evolve. With strong encapsulation, we can close off all access to the internal APIs of the JDK simply by not exporting the packages that contain them. Now, if we did that right away, we would definitely break a lot of existing code. So we're taking a more gradual, nuanced approach. Since migration takes time, especially in such a large ecosystem, starting with JDK 9, and at least through JDK 12, 13, something like that, if your code uses JDK internal APIs, then it will not compile, and it may generate warnings at runtime. Now, by your code here, I mean not just the code that you write yourself, but all those libraries that you pull down from Maven Central. We've deliberately relaxed the strong encapsulation of internal APIs in legacy packages for now at runtime so that old code continues to work. We'll eventually strengthen the encapsulation of these packages once we've provided standard APIs for the critical internal APIs and once everyone has had a chance to fix their old code. When we do that, in some future release, code that uses JDK internal APIs will not run. In the meantime, here's an example of the kind of warning you might see if you haven't seen one of these already. This is a log of starting up Jython. It's a Python interpreter written in Java running on JDK 9. What does this tell you? Well, it tells you an illegal reflective access operation has occurred. It identifies the code responsible and the internal API that it accessed. It suggests that you report this error to the maintainers of the errant library so you can do your part to help the ecosystem move forward. It tells you how to get additional warnings if you want to see them, because by default, only the first such warning is displayed. And finally, it reminds you that all illegal access operations will be denied in a future release. To help you get ready for that future, when such code will not run, we introduced a new tool in JDK 9 called JDEPS. If you run JDEPS against an existing jar file with the JDK internals option, then it can detect most uses of internal APIs. As an example, here it detected the use of sun.security.x509.x500 name. That's a mouthful. It is an internal API, and the tool even suggested a standard replacement, JavaX security auth x500 . Note that that replacement has been available since Java 1.4. Java 1.4 shipped in 2002. That was, what, 17, 18 years ago? So there's really no excuse not to be using it. Anyway, JDEPS, highly recommend that you use it. So the modular platform does break some things, but it doesn't break everything. In fact, if your code uses only standard Java SE APIs, then it most likely will work without change. We have removed a few obscure, rarely used methods and mechanisms to enable that clean modularization. We've also made a few very small behavioral changes that honor the specification, but are changes from how a few APIs used to work in the past. If you want to know more, have a look at JEP 261 on the OpenJDK website. It lays out all the compatibility-related changes in great detail. And beyond that, if you want to learn more about Java modules and the modular platform, I can recommend all 3 of these fine books. The modular platform enabled the second big change of the past year. We've reduced the platform by actually removing things for the first time in Java's history, or at least the first time on purpose. We removed the Java EE and Corba modules in Java 11. Why? Well, the details are in JEP 320, but in a nutshell, all of these components were costly to maintain. They were the source of multiple security vulnerabilities, and nowadays they're either available elsewhere, as in the case of Java EE, which is now at Eclipse, or they're no longer relevant, as in the case of Corba. We removed some other smaller things too. As I mentioned, in order to get that clean modularization of the platform, we removed some fairly obscure methods in Java 9. Most of these had to do with configuring property change listeners in various core APIs. These probably never should have been added in the first place, but there they were. We removed them only after analyzing lots of code out in the wild to see if anyone was using them, which hardly anyone was. While we were at it, we also removed a pointless constructor that accidentally slipped into Java 8. We removed more methods in Java 10. All of these methods were ill-defined, actively harmful, don't work, or don't do anything useful. We removed yet more such methods and one entire class in Java 11. Now, removing things can cause breakage, but to ease that pain, we always give advance notice by deprecating APIs to be removed, at least one release in advance, and often more than that. As an example of that advance notice, here are all the APIs deprecated in Java 11 for removal in a future release. These include many finalized methods in the core APIs, which we're removing since finalization is a fundamentally broken mechanism that we've replaced with something better. Now, when an API is deprecated for removal, that's always noted in the Java doc, and it's pretty easy to see. For example, here's a method called trace method calls. This dates all the way back to Java 1.0 when we only had bytecode interpreters. This method was intended for controlling method call tracing of a bytecode interpreter. It has been superseded by JVM-specific tracing mechanisms, et cetera, et cetera. Note the subtle and sophisticated specification, not implemented, does nothing. I don't think anybody's going to miss this one. If you compile source code that uses an API that's deprecated for removal, then the compiler will helpfully warn you about it. All right, popping back up. First, we modularized the platform, then we trimmed it down, and then we started moving it forward at a faster pace with a new release every 6 months. How can that possibly work? Let's look at the timeline. We shipped JDK 9 in September 2017, 10 just over a year ago in March 2018, 11 last September, 12 just last month, and 13 will come in September of this year, and so on, every 6 months, like clockwork. A feature release can contain any kind of feature, a language feature, a library feature, performance, a VM feature, a feature that removes an old feature. For this to work, features can go in only when they're nearly finished, because with a 6-month cadence, we can't afford to slip a release to fix a broken feature, as we used to do. But that's okay, because if a feature misses the current release, the next one is just 6 months away. It's no big deal. Now, at the beginning of all this was JDK 9, the final massive JDK release. JDK 9 contained 90 JEPs. We shipped it 3 years and 6 months after JDK 8, which shipped in 2014. There were 2 major slips to the JDK 9 schedule. Oracle engineers did much of this work, but not all of it. 6 JEPs came from outside Oracle by contributors from Red Hat, Linaro, and SAP, plus 2 independents, Doug Lee and Laurent Borges. These non-Oracle contributions included 3 entire CPU ports, some significant performance work, and an entire new 2D graphics rasterizer. So after all this stuff, what was going to be in JDK 10 just 6 months later? One worry we actually had about the 6-month cadence was we might have 0 features in a release. It might just be bug fixes and small enhancements because, well, it's going to ship in 6 months no matter what, right? Happily, that turned out not to be the case. JDK 10 contained 12 JEPs, including a language feature, local variable type inference, some more performance work, a massive refactoring of the source code into a single Mercurial repository, and a few other things. Now, again, Oracle engineers did much of this work, but 2 JEPs came from other contributors. Roman Kenke at Red Hat contributed a new GC interface, an internal interface inside the hotspot JVM. And some engineers from Intel contributed heap allocation on alternative memory devices. This pattern continued with JDK11. JDK11 contained 17 JEPs, including some long-needed JVM improvements, a new HTTP client API, the ability to launch single-file source code programs, which may seem just sort of cute, but it's actually really useful, and TLS 1.3 just in time for the final internet standard. Oracle engineers, again, did most of this work, but 3 JEPs were contributed by others. Some engineers from Bellsoft and Cavian contributed some ARM64 performance improvements. Alexei Shipilev at Red Hat contributed the Epsilon garbage collector, which actually isn't really a garbage collector. And Jean-Christophe Byler from Google contributed low overhead heap profiling. Moving on to JDK 12, which we shipped just last month on the 19th of March. JDK 12 contained 8 JEPs, including a micro-benchmark suite for the JDK itself, a preview language feature, switch expressions, and various VM performance improvements. Oracle engineers, again, it did most of this work, but in JDK 12 we do have an entire new real garbage collector, Shenandoah, contributed by Christine Flood, Roman Kenke, and Alexei Shipilev at Red Hat. As you can see, I think what has changed here isn't the rate of innovation. What has changed is the rate of innovation delivery. In 3 years, by 2021 or so, we probably will have merged around 90 JEPs, just as we had in JDK 9. These feature releases aren't just about JEPs, of course. Each release contains many smaller enhancements and bug fixes. As an example, in JDK 11, according to our bug database, we resolved almost 2,500 issues. Oracle engineers were responsible for most of those, but there were significant contributions from engineers at SAP, Red Hat, Google, a collection of individuals, and Bellsoft. Returning to our timeline. The 6-month cadence will enable Java better to compete with other platforms. But you might be wondering, what about updates? What about security fixes? What about critical patches? The plan in the OpenJDK community is to update the current feature release for at least 6 months. That's 2 quarterly update releases. And then every 3 years, we'll declare a long-term support release. So the first long-term support release was 11, which shipped last September. The next will be 17, which will ship in 2021. If you like, you can think of JDK 8 as sitting way up there about where the Devoxx logo is. That was the previous long-term support release. Each of these LTS releases will be updated well past the beginning of the next LTS release, and possibly even longer. Now, you might think that non-LTS releases are in some way experimental. Oh, it's just a fancy name for a beta release, I've heard some people say. But that's not true. Every release is production ready. What differs is only the support timeline. So, you have a new kind of choice to make. You can take the blue pill or the red pill. You take the blue pill and you wake up in your bed and continue to develop and deploy uncomfortable, conservatively managed, and slow-moving LTS releases with an update release every quarter and a major migration every 3 years. You take the red pill and you go down the rabbit hole where you can enjoy the latest language features, API enhancements, performance improvements, and bug fixes with a minor migration every 6 months. It's up to you. All I offer is the truth. If you do choose the LTS path and take the blue pill, you might be wondering who will produce your update releases. Again, you have a choice to make. Since JDK 9, Oracle contributors in the OpenJDK community have focused and will continue to focus primarily on feature releases rather than on updates. Oracle will ship OpenJDK builds under the GPL for the first 6 months of each feature release, the GA release plus 2 update releases, whether that release is a long-term support release or not. After that, Oracle will offer long-term support builds, but in a change from the past, these will be available only under a commercial license that allows free use for development and testing, but requires payment for use in production. Now, that might sound scary, but don't worry. Java is still free. All of the code is still available under the GPL for anyone to build, test, publish, update, and support. Oracle engineers won't regularly contribute to, much less lead the LTS releases as they have in the past, but that's okay. the OpenJDK community as a whole has a proven track record of transitioning the leadership of update releases from Oracle engineers to non-Oracle engineers. We did that years ago for JDK 6 and JDK 7. We did it again for JDK 8 and JDK 11 just recently when Andrew Haley, Red Hat's Java platform lead, took on the leadership of the JDK 8 and JDK 11 updates projects. This isn't just my personal fantasy. As Andrew has assured everyone, whether by Oracle or Red Hat or someone else, JDK LTS releases will continue to be supported. We all have a lot invested in Java, and we won't let it fall. The LTS work will carry on in the OpenJDK community as it has in the past. You'll be able to get carefully built, well-tested JDK LTS builds based upon that source code in almost any Linux distribution, whether derived from Red Hat, Debian, Gentoo, or Arch. If you're not on Linux, you'll be able to get LTS builds for free from a variety of providers. Now, for this plan to work, it's critical that you be able to switch from one provider to another. In the past releases, this wasn't possible because Oracle always held back a few so-called commercial features that were available only to paying customers. These included application class data sharing, Java Flight Recorder, Java Mission Control, and the Z garbage collector. To enable such switching and to establish a level playing field, over the past 2 years, Oracle open-sourced these commercial features so that Oracle builds and OpenJDK builds are now functionally interchangeable. You can switch from one provider to another as you please. When you choose a provider, though, you might want to consider those who, with the depth of knowledge that comes only from a long-term investment in the platform. So you have a choice. You can take the blue pill or the red pill. You can choose the conservative LTS path with the blue pill and prepare for a major migration every 3 years. This can be a good choice for conventional enterprise-style deployments of large applications on large servers. Or you can choose the fast-moving feature release path and take the red pill with a small migration every 6 months. This can be a good choice if you're deploying to the cloud or to app stores. If you choose the LTS path and take the blue pill, then you shouldn't ignore the non-LTS releases. Some free advice. If you maintain an infrequently migrated system, then you should still test it with each non-LTS release. That way you'll be ready for the next LTS release by the time it's available. You're essentially spreading your migration effort out over time. If, on the other hand, you choose the adventurous feature release path and take the red pill, then you're going to migrate to each feature release as it becomes available. So make sure that your tools and dependencies can keep up. Many will be able to keep up, but some won't, especially if they're no longer maintained. So plan with care. To sum up, we're evolving the Java platform at a more rapid pace in order to keep up with competing platforms. We have broken a few things and will continue to do so in order to make Java a better fit for modern applications. Are these changes really all that scary? No, I don't think they are, for 4 reasons. First, we'll always give advance notice before removing anything, and we'll only do so when there's a very good reason. We don't want to break existing code unnecessarily. Compatibility remains one of the core values of the Java platform. Second, you have a choice to make, which you didn't have before. You can take the blue pill and migrate every 3 years at a comfortable stately pace, or you can take the red pill and enjoy the latest features and fixes every 3 months. It's up to you. Third, it's true that Oracle will no longer provide free long-term JDK updates, but Java is still free. Free updates will be available from a variety of other providers, including all of the major Linux distributions. If you want active support, then you're probably you're either going to have to pay someone or else do it yourself. But that's always been the case, so choose your provider wisely. Finally, we did break a few things. Migrating past Java 8 may require some work, but it might not be as hard as you think. All 3 of the major IDEs already support all of the new language features, even the ones in 12. Many popular tools, libraries, and frameworks already support JDK 9, if not JDK 11 or even 12. You don't have to take my word for it. Just after Java 9 was released, I asked on Twitter, do you maintain a popular Java library, framework, or tool? If it works fine on JDK 9, then please reply with its name and version. That was way back in 2017, so shortly after JDK 11 was released last fall, I asked, Do you maintain a popular Java library, framework, or tool? If it works like heaven on JDK 11, then please reply with its name and version. My thanks to Sam Brannon of the JUnit team for that hashtag. I saw many responses to this. All 93 of these libraries, frameworks, and tools work just fine on JDK 9. Many of them worked without change, or they required minor changes which their maintainers made pretty easily. These include the standard build tools, Ant, Maven, and Gradle, popular test frameworks, JUnit and TestNG, popular libraries, ByteBuddy, Juke, Jackson, Log4j, Hibernate, and Netty, and the entire Spring framework. 51 of these components work not just fine on JDK 9, but like heaven on JDK 11. Since the transition from 9 to 11 is much easier than the transition from 8 to 9, I expect the rest of them will catch up in short order. My most urgent advice to you today, then, is this. If you're using Java 9 or later, upgrade to the latest versions of all your tools and dependencies, because everything changes and nothing stands still. Now, as I said earlier, the biggest change with the 6-month cadence is not the rate of innovation, but rather the rate of innovation delivery. Let's now take a look into the future, if we can, both near-term and long-term, to look at some recently delivered innovations and some that are still in the pipeline. At the meta level, though, how do we decide what features to add to Java? Do we just add stuff because it's cool, because other platforms have it? No, we actually have principles by which we drive Java forward. For almost 24 years with Java, we've been pursuing two big goals. The first is developer productivity. Java is about helping developers build and maintain large and reliable programs. It's not about one-off scripts that you write one day and throw away the next. It's about building things for the long haul and being able to maintain them over the long haul. The other big goal is program performance. Program performance, of course, is measured in many ways. We measure time in the form of startup latency and throughput. We measure space, static storage space as well as dynamic space in memory. There's the whole issue of scalability. We would like Java to scale from iPhones up to Big Iron. For almost 24 years, we've pursued these two big goals in the face of constantly evolving factors, including new programming paradigms such as mixed functional and object-oriented programming and data-oriented programming, evolving deployment styles to clouds and to application stores, and of course, evolving hardware. Hardware. We have machines with terabyte memories, deeper memory hierarchies, deeper and more numerous processor pipelines, and vector and SIMD instruction sets. We're pursuing these goals in light of all of these factors in some of the major active projects in the OpenJDK community. These are Amber, which is about right-sizing language ceremony, being led by Brian Getz. Loom, bringing fibers to the Java platform and the JVM. And Valhalla, value types and specialized generics, being led by John Rose and Brian Getz. Sorry, I forgot to mention, Loom is being led by Ron Pressler. Let's start with Amber. Right-sizing language ceremony, what does that mean? Well, in a way, it's about reducing boilerplate, one of the big pain points of Java, all of this boilerplate. Boilerplate is especially painful in the modern era of data-oriented microservices. The solution brought by Amber is not aimed specifically at boilerplate reduction. If we just wanted to do boilerplate reduction, we could transform Java into APL and everything would become packed but unreadable. We're not going to do that. Amber is a series of language features delivered over time. They're intended to leverage each other that let you express more clearly what you mean, more clearly and more succinctly. And then the boilerplate, we find, just tends to take care of itself. Here, let's take a look at one example. How many people think Java doesn't have type inference? Oh, good, a very educated audience. Java does have type inference. A lot of people think it doesn't. And it's true that in the beginning, Java did not have type inference, but we started adding some type inference in Java 5 when we added generics. If we hadn't had type inference with generics, then when you invoke a generic method, you would have had to type this ugly string thing to indicate the return type of the method you're invoking. Nobody wants to do that, and the compiler bloody well knows what to do, so it does a little bit of inference and figures it out for you. In Java 7, we added a little more type inference. List string list equals new array list of string. You don't actually have to type string in pointy brackets twice. You can just use the diamond operator on the right-hand side because the compiler can tell exactly what belongs in those pointy brackets on the right-hand side because you already typed them on the left-hand side. In Java 8, with lambda expressions, you can write down the type of a lambda parameter, string s in this case, but you don't have to. In many cases, that's just extra noise. It's perfectly clear what the type of that is going to be. The compiler can tell, so it will infer it for you if you don't say what it is. In Java 10, we introduced local variable type inference. Take a very simple example. We've all written this code. Buffered reader equals new buffered reader, new file, reader file, da 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 da. Yeah, okay, I get it. There's a buffered reader involved. Why am I having to read this so many times? In 10, with local variable type inference, you can use a new keyword called var and just type that. So var reader equals new buffered reader. The compiler infers from the right-hand side what the type of the new variable will be. This is for local variables only. You can't use var on fields. You can't use var on method parameters. It's not dynamic typing. We have not converted Java into JavaScript. They still have nothing to do with each other. Cars and carpets and all that. So it's not dynamic typing. It's just better static typing and much less keyboard typing for you. But because it is less typing, you probably ought to be a little bit careful, maybe a little bit more careful when you choose variable names. If we take a longer example, you've got a URL, you want to open a connection, you want to wrap a scanner around that, and yes, you can type all these type names twice, or you can just use var, and it looks much nicer. But if you used very short variable names on the left, then later on down in your code, it might be pretty confusing. So use them with care. Local variable type inference was introduced in Java 10. The details about that are in JEP 3.26. Let's look at some more Amber features, some more boilerplate reduction. Suppose you've got a simple enum for the days of the week. Now, suppose we want to compute the length of the name of each day. Given an instance, we want to compute the length of its name. Now, we could cheat and use toString, but we're not going to do that. For the case of this example, we're going to write a switch. So you've got a switch, you switch on a day object, Monday, Friday, Sunday, the answer is 6, you assign that to this numLetters variable, and so on for these other cases. Now, all kinds of things can go wrong here. You can forget a break. You can forget to assign to the variable. You can forget the default, and everything just falls through. As my colleague Brian Getz likes to say, this isn't the language helping you out. This is the language daring you to make a stupid mistake. We're just computing an expression, so let's write it that way, for heaven's sake. And in Java 12, you can. You can use switch. You can write a switch expression. So it's not a statement anymore. It's an expression that returns a value. You have your cases. We borrowed the arrow syntax from Lambda to indicate the result. And a really cool thing about it is that if you're switching on an instance of an enum type, the compiler can do enough analysis to determine that you don't need a default. Now, if I'd forgotten one of these, the compiler would issue an error message saying I either need a default or I need to include more cases. But since I included them all, this is all good. So it's much clearer, and it's also much more compact. So as I said, this is in Java 12. Details are in JEP 3.25. It is what we call a preview feature. So it's not enabled by default. We think it's like 98, 99% done, but we want to take one of these 6-month releases and use it to get some additional feedback. So if you're interested in it, try it out. If you see problems with it, please let us know. If you do want to play with switch expressions, then you need to use this enable preview option at both compile time and runtime to enable it. All right, let's move on to features that are not yet in any early access build. How many people have written code like this? Yeah, it's pretty ugly, right? I mean, you've got double quotes on each line, you've got pluses, you've got embedded new lines. This is pretty horrible. Oh, and there are double quotes embedded in there, so you have to quote the double quotes with backslashes, and if you forget those, then you lose. Yeah, wouldn't it be nice if Java had multi-line string literals? Okay, well, let's do that. So this is another feature in development now. This has been through a few iterations. If you were paying careful attention, we almost had an earlier version of this in Java 12 as a preview feature, but we pulled it at almost the last minute because we became convinced that we did not have the right design. This is an example of the design we're currently pursuing, borrowing this triple quote syntax from other languages. You type your text, you can have, it's got new lines in it, you just have the triple quotes at the beginning, the triple quotes at the end. You know, if you need triple quotes in the beginning, then okay, then you'll have to use concatenation or something to break them apart. But that's where we're headed with this. We are aiming for Java 13 as another preview feature. Oh, and right, there's this handy align method here to deal with alignment, because you probably don't want all of that indentation to wind up in your resulting string. So aiming for 13 in a new JEP, not quite written yet, also as a preview feature, but no promises. I'm confident, though, that we will get there. Maybe. No promises. All right, let's look at another classic boilerplate issue in Java. Plain old Java object, class point. It's got an X, it's got a Y, it's got a constructor, it's got accessors. Is this class complete? What is it missing? Equals hashcode and toString. Yes, you've got to write those too. Now, IDEs can generate these for you, but that doesn't help with reading the code, you know, a year later when you or someone else is trying to maintain it. It makes it easy to cut corners, and cutting corners leads to bugs, and bugs lead to pain, and we know all that. The thing about this is, all the encapsulation provided here by this class isn't actually necessary. We need a way to say that this class is just a transparent container for some data. With records, you can do just that. You replace all of that Pojo code with just one line, because sometimes data is just data. It's okay, we don't need to encapsulate anything. Now, you can customize records if you want. You can define your own hashcode method. You can define additional methods if you want the norm value of a point, for example. You can customize the constructors to check invariance. What you can't do is add more state. You can't do that because it would violate the invariant that a record is just a transparent holder for data. Now, records are immutable, and if that doesn't work for you, well, you can always write a class. But in many, many of the use cases that we've looked at, having them be immutable is perfectly fine. We do have a prototype implementation of records, although it's not in any early access build just yet. So that's a selection of features from Amber. Let's now move on and take a quick look at Loom, which is fibers for the Java platform. Let me do this quick switch here. I love it when technology works. Okay, so fibers. Let's look at some actual code. I've got an early access build here, well, a prototype build actually. Java-version Loom built just a few days ago, derived from JDK 13. Let's drop into JShell and take a look around. So fibers are kind of like threads, but they're different. What problems with threads do our fibers aim to solve? Well, threads, you know, we know what threads are. We've had them around for many years. You can make yourself a thread. You can give it a runnable. Oh, whoop. We do this. Whoops. Very good. We start the thread. What's it going to do? Oh, it prints hi, big deal. Yeah, we know all that, but threads have a lot of baggage. They've got all these methods. Threads have thread groups that are basically useless. They have priorities that are mostly ignored. They've got this context class loader thing, which is extremely awkward. Threads are associated, Java threads are associated with operating system threads, so they're expensive to create. It's expensive to switch context. It takes thousands of instruction cycles to switch from one thread to another. Because of that, people turn to doing more awkward but faster things, such as non-blocking or asynchronous I/O, which can be much, much faster, but it's notoriously difficult code to write and to maintain. Because of that, in many cases, people just use threads because they're easier, but servers wind up being underutilized. So fibers are a lot like threads, but they're lighter weight. Let me show you how to make a fiber here. We'll make a fiber. When you make a fiber, it gets scheduled and run right away with this static schedule method. Whoop. I can't type today. Boom, it prints hi, and then it's done. And it returns we get the fiber object back. Note that it says here no carrier thread. That means that the fiber is no longer associated with an operating system thread. Fibers are lighter weight because the Java runtime system dynamically maps them to operating system threads as needed. The runtime system can switch from one fiber to another in just a couple of hundred instructions, which is much, much faster. Fibers are simpler than threads. If we look at the methods on a fiber object, aside from the methods that are inherited from Java lang object, there are just a few. You can wait for a fiber to terminate, you can cancel a fiber, you can ask whether it's alive, you can ask whether it's canceled, you can join a fiber. You can also convert a fiber to a future. Fibers play well with completable futures. So I'd like to show an example of migrating to fibers in some actual code. So let's look at some code in my favorite IDE, namely Emacs. Source main Java Loom sleep service. So we're going to make a stupid tiny REST service using JAX-RS. It's on the path called REST sleep service. You invoke this. You can give it a count in milliseconds, and it will just sit there and sleep for that long. Big deal. Why is this interesting? Well, what we're going to do is run this in Jetty, which is a non-blocking, lightweight non-blocking web server, and then we're going to use a load tester to load that server with 1,000 requests per second and see how it does. For each request, Jetty is going to have to hang on to a thread for 100 milliseconds, and we'll see what happens. So I come up here, and it's all encapsulated in a make file. We build it. Builds, we run it. This is using the Vegeta load testing program. It warms up for 5 seconds, runs it for 10, and then we'll go look at a graph of how it did. Okay, well, that's pretty horrible. This response times went as high as 1.3 seconds because switching between threads is just extremely expensive. Now, to convert this to use threads, it was actually very simple. With Jetty, Jetty's extremely cool. You configure it by writing some actual Java code. To have it do something other than threads, you just give it a new thread pool, which only needs to be able to execute a runnable, not actually provide an actual thread. So when Jetty needs to execute a runnable now, we schedule a fiber for it, and we're done. So let me make fibers. We do the same test, but now using fibers. And we reload this, and the orange line is the fiber response time. Now, that's actually kind of hard to see, so let's zoom in. The fibers start out with a couple of peaks here. That's probably when some code is being compiled by the runtime compiler. After that, it settles down, and it's rarely taking much more than 100 milliseconds all the way through the entire 10-second run. All right, so that's a quick look at Loom. I'm afraid there won't be time for Valhalla. I will end by noting that if you have questions, I'm doing a Q&A session tomorrow at 13:30 in Paris 242. Don't believe a word I've said. Thank you very much.